The Webb glance is such a long way out that it's catching light that has been voyaging for over 13 billion years. Yet, the universe has been expanding, and thus the light has been stretching as well. For the most distant worlds, we're looking back in time, nearly to the Big Bang. The immensity of the universe might seem vast, but every last bit of it started from what we allude to as the singularity. As of now, this is how we understand the Big Bang hypothesis. Anyway, the James Webb Space Telescope, JWST, has revealed significant mysteries about the birth and development of the universe, leaving us dumbfounded. Prestigious physicist Brian Cox has proclaimed that the noteworthy discoveries made by the JWST might actually reshape our understanding of the universe as a whole. Join us as we dive into these new heavenly discoveries that promise to change our comprehension. The James Webb Space Telescope, named after the recognized NASA executive James E. Webb, stands as a wonder in current galactic investigation. This telescope represents a huge mechanical leap forward from its ancestor, the Hubble Space Telescope, resulting from a cooperative effort between NASA, the European Space Agency, and the Canadian Space Agency. The JWST surpasses the abilities of its predecessor. It utilizes cutting-edge technology and a design enhanced for focusing on the universe in remarkable detail. Unlike the Hubble, the JWST delivers clear and sharp images of far-off celestial bodies. Working primarily in the infrared range, this fascinating feature allows it to penetrate astronomical dust and capture celestial objects that were previously hidden from our view. With its massive 6.5-meter primary mirror made of 18 hexagonal sections, the JWST far exceeds the Hubble's reflector size. Positioned roughly 1.5 million kilometers away from Earth at the second Lagrange point, L2, it orbits the Sun in harmony with Earth, ensuring a stable and continuous view of the cosmos. Looking into the far-off corners of the universe involves exploring not only light years but also a type of time travel. The JWST uses infrared instruments to observe celestial objects and events going back billions of years. Because of the expanding universe, the light emitted by these objects undergoes redshift, shifting from the visible spectrum to the infrared. Fortunately, the JWST can detect infrared light emitted by objects at extreme distances, enabling scientists to study the birth of stars, investigate galaxy development, and examine exoplanet atmospheres. Its latest historic discovery involves identifying an inconceivably massive collection of galaxies at the edge of the observable universe. This finding challenges the validity of existing theories about cosmic formation, prompting a reassessment of our fundamental cosmological assumptions. To understand how we arrived at this point, let's take a brief journey through the history of space exploration. Early civilizations, like the Greeks and Chinese, laid the foundation for understanding planetary movement by observing celestial bodies. Newton's laws in the 17th century provided a theoretical framework for space travel. In the mid-20th century, Edwin Hubble, an influential astronomer, made historic contributions to cosmology and observational astronomy. His observations revealed that distant nebulae were actually separate galaxies, far beyond the Milky Way, revolutionizing our view of the universe's size and expansion. Hubble's law, established by him, showed that galaxies farther away are moving away faster, providing evidence for the universe's expansion. The post-World War II era marked the beginning of the space race, with the Soviet Union's Sputnik launch in 1957 as the first artificial satellite in orbit. Yuri Gagarin's orbital flight in 1961 and the Apollo 11 moon landing in 1969 were major milestones. Fast forward to 1990, the Hubble Space Telescope was launched, delivering exceptional clarity and breathtaking insights into the universe. The journey from ancient stargazing to the James Webb Space Telescope showcases the constant evolution of our cosmic understanding. Hubble revealed the vastness of space and revolutionized fundamental ideas in astronomy. Take, for example, the famous Pillars of Creation image in the Eagle Nebula, which revealed a star nursery formed by towering columns of gas and dust. Another milestone was the Hubble Deep Field, capturing thousands of galaxies in what seemed to be an empty patch of sky. The HST also studied exoplanet atmospheres, detecting water and organic molecules on distant worlds, hinting at the potential for habitable zones beyond our solar system. By following the development of the nearest observed supernova, SN 1987A, Hubble illuminated the life cycle of massive stars. These achievements cemented the HST's legacy as a cornerstone of modern cosmology. Its successor, the James Webb Space Telescope, was launched to build on these technological advancements and refine our model of the universe's origin. Today, the prevailing theory of the universe's beginning states that around 13.8 billion years ago, it started as an extremely hot and dense singularity. Rapid expansion followed, creating matter, energy, and the fundamental forces. As the universe expanded and cooled, atoms, stars, galaxies, and large-scale structures formed. The Big Bang theory also explains the cosmic microwave background radiation, the abundance of light elements, and the universe's large-scale structure. Despite being widely accepted today, the Big Bang theory initially faced skepticism. Alternative models like the steady-state theory suggested a universe with no beginning. Questions about evidence for the singularity, the expansion, and observational anomalies were common. Many of these objections were addressed over time, with a key breakthrough in 1965, the discovery of cosmic microwave background radiation, predicted by the Big Bang model. Missions like COBE and WMAP, along with technological advancements, reinforced the theory. Accurate measurements of cosmic microwave background radiation matched theoretical predictions. Now, with the JWST, equipped with advanced infrared instruments that can peer through cosmic dust, we can view the oldest light in the universe and observe objects formed shortly after the Big Bang. Its infrared capabilities allow it to study star-forming regions, stellar nurseries, and young stars hidden from optical telescopes. Infrared light, with longer wavelengths than visible light, can penetrate interstellar dust, overcoming a key limitation of the Hubble Space Telescope. The JWST can also observe cooler objects that emit mainly in infrared, making it ideal for studying exoplanets, brown dwarfs, and distant galaxies. As celestial bodies move away, the light they emit is stretched, redshifted, toward longer wavelengths. The JWST's infrared sensors can detect this redshifted light, capturing the earliest signals from the universe and offering insights into its formation and evolution. Energetic events such as black hole mergers or the birth of new stars emit primarily in the infrared, expanding the JWST's scientific range. It supplements optical telescopes like Hubble by offering greater sensitivity and the ability to detect faint infrared radiation. This enables it to peer deeper into space and provide a more comprehensive picture of cosmic history. The JWST is our window into the early stages of cosmic evolution. Recently, it revealed something so astonishing that it could prompt a reconsideration of the entire cosmological model. The discovery of such mature and massive galaxies in the early universe suggests that galaxy formation may have begun far earlier and proceeded much faster than previously believed. Some of these galaxies appear to have structures, sizes, and masses that rival or even exceed that of modern-day galaxies, an observation that has taken cosmologists by surprise. This rapid development contradicts the hierarchical model of galaxy formation, which posits that small galaxies gradually merged over billions of years to form larger ones. Instead, the James Webb Space Telescope's data hints at a universe where complex structures emerged much more swiftly, possibly within a few 100 million years after the Big Bang. Astrophysicists are now exploring several possibilities to explain these anomalies. Dark matter dynamics. The role of dark matter in early galaxy formation might be more significant than expected. Perhaps dark matter clumps formed gravitational wells that accelerated the birth of massive galaxies. Modified cosmic inflation. The inflationary period immediately following the Big Bang might have varied in intensity or scale, producing denser regions in space where galaxies could form more rapidly. Alternative cosmologies. Some theorists are entertaining alternative models, including varying physical constants or even cyclic universe theories, where the universe undergoes repeated expansions and contractions. Furthermore, JWST's ability to analyze the chemical composition of these early galaxies adds another layer of intrigue. Some galaxies show surprising levels of metallicity, elements heavier than hydrogen and helium, which are typically produced in later generation stars. This suggests that multiple generations of star formation may have already occurred within these early galaxies, a process thought to require far more time than the current cosmological timeline allows. These revelations may force scientists to refine or even overhaul sections of the lambda-cold dark matter (CDM) model, the prevailing framework used to describe the evolution of the cosmos. If galaxies formed earlier and more efficiently than predicted, it could indicate gaps in our understanding of dark energy, dark matter interactions, or even gravity on cosmological scales. In response to these paradigm-shifting discoveries, physicist Brian Cox and others have emphasized the need for humility and open-mindedness in the face of new evidence. Every time we've looked deeper into the universe, Cox noted, we've found surprises. The JWST is reminding us that the cosmos is more dynamic, more complex, and more astonishing than we ever imagined. As the James Webb Space Telescope continues its mission, scanning deeper into the abyss of space and time, it promises to deliver more transformative insights into the origins, structure, and destiny of the universe. Whether it confirms existing theories or leads to entirely new frameworks, one thing is certain: we are witnessing the dawn of a new era in cosmology. An unfathomable mass of galaxies challenges the assumed distribution and arrangement of large structures, revealing a more intricate and denser cosmic web than previously thought. These observations raise fascinating questions and avenues for further exploration. The existence of large structures challenges early models of cosmic structure formation, prompting researchers to refine models for a better explanation. Understanding how such vast structures gathered rapidly after the Big Bang presents a puzzle that requires an explanation that doesn't violate fundamental principles of cosmology. Significant disparities in the conditions of the early universe, compared to predictions based on existing models, have also been revealed. These differences could suggest previously unknown physical processes, unexpected conditions, or unidentified cosmic phenomena. In simple terms, these variations have prompted scientists to rethink and improve our models of the universe. Currently, all we can do is say that further exploration is required to incorporate these surprising observations into a more comprehensive understanding of the universe. Initial observations often provide exciting glimpses into the universe, but investigations sometimes reveal differences. For example, early observations may show specific properties or arrangements within distant galaxies that, upon closer examination, reveal fluctuations in their composition, structure, or evolutionary pathways. In conclusion, enormous phenomena are incredibly complex and require careful investigation for us to accurately understand their true nature. Spectroscopy, a method that helps unravel the properties and history of celestial objects, is an example. It involves analyzing the light emitted or absorbed by astronomical objects. By examining the properties of the light, spectroscopy provides detailed information about the chemical composition, temperature, density, and movement of celestial bodies. This analysis helps us understand the origins, development, and contributions of celestial bodies to the cosmic tapestry. The JWST has uncovered numerous cases where initial observations differed from later investigations. For instance, initial observations of distant galaxies suggested a simple structure primarily dominated by lighter elements like hydrogen and helium, in line with theoretical expectations. However, spectroscopic analysis using the JWST showed fascinating variations in elemental signatures, identifying heavier elements or compounds previously undetected or misunderstood in the early universe. This challenges conventional ideas about the early universe's chemical composition and the mechanisms responsible for their development and dispersion across vast distances. Similarly, initial assumptions about galaxies in the early universe were based on preliminary observations suggesting a relatively uniform pattern of development and organization. However, more detailed investigations by the JWST revealed a much more diverse and complex array of chemical compositions within these galaxies. The James Webb Space Telescope continues to redefine our understanding of the cosmos by shedding light on previously hidden corners of the universe. One of its most exciting capabilities is its ability to study exoplanets in unprecedented detail. By analyzing the atmospheres of planets orbiting distant stars, the JWST can detect crucial chemical signatures, such as the presence of water vapor, carbon dioxide, methane, and other organic compounds. These findings provide valuable insights into the potential habitability of exoplanets and the conditions that might support life beyond Earth. In addition to exploring distant worlds, the JWST is transforming our understanding of star formation. It can observe the birth of stars in regions where young stars are surrounded by dense clouds of gas and dust, which optical telescopes cannot penetrate. With its ability to detect infrared light, the JWST captures the faintest glimmers of these new stars as they emerge from the darkness, offering a clearer picture of the processes that lead to star and planetary system formation. By studying these regions, astronomers are gaining a deeper understanding of how stars like our Sun come into existence and evolve over time. Another remarkable aspect of the JWST's research is its ability to peer into the hearts of galaxies. Black holes, particularly supermassive ones, are believed to reside at the centers of most large galaxies. JWST's advanced instruments allow scientists to observe the behavior of matter around these black holes, providing new insights into their growth, their influence on galactic evolution, and the powerful jets of energy they emit. These findings are helping astronomers piece together the story of how galaxies and their central black holes evolve together, influencing each other's growth. Moreover, the JWST discoveries are not only answering long-standing questions but also raising new ones. As it probes deeper into the history of the universe, it is uncovering phenomena that challenge existing theories and models. These challenges drive the scientific community to redefine current cosmological models and open up new avenues for research that were previously unimaginable. The discoveries of the JWST are not just pushing the boundaries of what we know, they are helping to reshape the fundamental principles of how we view the universe itself. As the James Webb Space Telescope, JWST, continues its mission, it is also helping bridge the gap between theoretical predictions and empirical evidence. The clarity and depth of its infrared imaging allow astronomers to revisit long-standing hypotheses, either reinforcing them with new data or prompting their revision entirely. This feedback loop between observation and theory is crucial to scientific advancement and ensures that our models of the universe remain dynamic and responsive to new findings. For instance, the JWST has identified early galaxy formations that appear much more mature than previously expected based on existing timelines. These galaxies exhibit complex structures, including well-formed spiral arms and dense stellar populations, far earlier in the universe's history than models predicted. Such observations suggest that galaxy formation may occur more rapidly and under different conditions than previously believed, challenging our understanding of the timeline and mechanics of cosmic evolution. Furthermore, the JWST's precision has led to the detection of previously unknown star clusters and protogalaxies at the farthest reaches of the observable universe. These discoveries provide critical data points for mapping the universe's expansion and understanding the role of dark matter and dark energy in shaping the cosmic landscape. In addition to these large-scale discoveries, the JWST is making significant strides in studying planetary systems closer to home. Its ability to monitor changes in the atmospheres of gas giants, ice worlds, and potentially habitable exoplanets offers new opportunities to study planetary weather patterns, atmospheric escape processes, and chemical evolution over time. The telescope's impact is not limited to distant and exotic objects, it also brings a new level of insight to our own solar system. Observations of planets like Jupiter and Saturn, as well as their moons, have revealed unexpected thermal patterns and chemical signatures, offering new perspectives on planetary dynamics and internal structures. As more data pours in, international teams of scientists are collaborating to analyze and interpret the findings. The scale and complexity of the JWST's observations require interdisciplinary approaches, blending astrophysics, planetary science, chemistry, and data science to extract meaningful conclusions. This collaboration is fostering a new era of cooperative discovery, where shared resources and open data accelerate scientific progress across borders. Ultimately, the JWST represents a monumental leap forward in our quest to understand the universe. Its discoveries are not only deepening our knowledge but also igniting a renewed sense of wonder and curiosity about our place in the cosmos. With each passing observation, the telescope is peeling back layers of cosmic history, revealing a universe that is far more dynamic, diverse, and mysterious than we had ever imagined.